Welcome back. Now we are going to look more deeper into the chromatograms and the realization of different chromatographies. So, firstly, there are really very many types of analytical chromatography, and actually, the separation of these chromatographies also varies. So, most simple is the is the dividing the types of chromatography based on the mobile phase. And you will hear about this a lot. You will hear about people saying about liquid chromatography and gas chromatography. These are the most common ones. But there is also supercritical fluid chromatography, so SFC, um, as an abbreviation, and this is also using supercritical fluid as a mobile phase. Liquid chromatography uses normal solvents as the mobile phase, while gas chromatography uses different gases. In addition to mobile phase, also the types of interactions that are used to separate, distinguish between the compounds that are in our complicated sample mixtures can vary. So, for example, we can have partitioning chromatography, which is actually the most common type of chromatography, both in gas chromatography and liquid chromatography today. We can also have adsorption chromatography, which is nowadays used mostly to separate different very volatile molecules in gas chromatography. Or we can have ion chromatography, which is a subcategory of liquid chromatography where we are specifically separating ions based on the ionic interactions. And chromatographies can also be separated based on the technical realization. Most broadest categories are column chromatographies versus planar chromatography. So TLC, thin layer chromatography, falls to the planar chromatography category, which you have probably used in organic chemistry before. Column chromatography, on the other hand, can be divided further into capillary chromatography, which is mostly used in gas chromatography, or then to the fill particle columns, which are mostly used in liquid chromatography. But for example, in liquid chromatography, we also have further deviations depending on which kind of pressures we use, which kind of performance we gain into high performance and ultra high performance liquid chromatographies. So there are really many subcategories, and this is all because separating the mixtures is so important in analytical chemistry, and very many different techniques have been developed to gain as good separation as possible. And when we think, when we go into the separation, then it's important to um, once again remind what are the two main actors in our chromatographic system. These are the stationary phase and the mobile phase. So in stationary phase, we mean the material that is filling the column, and this is the material that is kind of immobilized in the column. It doesn't move anywhere. That's why it's stationary. And this is a very big player in the chromatographic separation, because what is happening in the chromatography is that as our analyte molecules travel through the column, they are getting close to the stationary phase, they interact with the stationary phase, so we can say that they bond with the stationary phase, and then they are again released. So this bonding and releasing is very important in chromatography, because some compounds which are interacting stronger, for these compounds, this bonding and releasing events are happening more frequently, and therefore they are slowed down in the column, so they don't move through the column as fast as the mobile phase does, as fast as the compounds which are not interacting with the stationary phase so strongly. So the more frequently the bonding release occurs, the stronger this interaction is, and the longer the columns it will take the compounds to pass through the column. And the separation of the compounds in chromatography is based on the fact that for different compounds, these interactions with the stationary phase are of a different strength, and therefore they are also being able to separate, because some compounds go through the column very fast, while for other compounds they are very strongly bound to the stationary phase, so they are very often and very long retained by the stationary phase, while other compounds are not, and they go through the column very fast or faster. Another important player is the mobile phase. So this is the fluid that is carrying our sample through the column. And the mobile phase can itself also interact with the stationary phase, but its main purpose is to carry the sample through the column. And the most common mobile phases are liquids or gases. Supercritical fluids are also possible. So when we have this nice separation process of the different components of our sample based on the different interaction with the stationary phase, aided by the mobile phase, which is carrying our sample compounds through the column, then we can register this process on a chromatogram. And this we can do when we have a detector that is at the end of our column, which measures the compounds that are coming out from the chromatogram. And this coming out from the column we call eluting. So compounds are eluting from the column. And the detector can be used to measure the elution of the compounds. When we have complicated mixtures, then we want to separate them as efficiently as possible. And ideally, this means that for each compound in the mixture, we have 1 peak. This, however, is mostly not achieved, especially when we have very complicated mixtures. This doesn't mean that chromatography is not doing its job. However, as a combination of the chromatography and the detection system, we are very, very often able to achieve a sufficient selectivity which neither of these alone might not be able to achieve. And the largest challenge, or the research question, or also a question to the analytical chemists who carry out chromatographic tasks in industry or regulatory laboratories, is to achieve this separation in the chromatographic system, to achieve the best separation of the compounds in these mixtures. So how to measure this performance of the chromatographic system? How can we describe it? How can we say how good is our ability to separate the compounds? Let's start with the basic concept. So here is a chromatogram of one single compound. And there are a few important definitions that we need to keep in mind. So the first one is the retention time of the compound. And this is the time that it takes for the compound to pass through the column. And we measure this by starting a stopwatch at the moment we insert the sample to the column. We call this inject. So we inject the sample to the column. And when the maximum of this compound peak, so this is the peak of the compound, is coming out at this time, we close our stopwatch and we say, okay, this was the retention time of this compound. So that is the retention time of our analyte that we are interested in. We also have something which is called a dead time. So either T0 or Tm, which means the time that it takes for a compound or mobile phase that is not interacting with the stationary phase to pass through the column. So this is just simply flow through the column time. And for the fact, due to the fact that it takes time to pass through the column, even if no interaction between the analyte and the stationary phase would take place, so because of this dead time is occurring, we define something which is called a retention factor. So this is essentially how much longer does it take for the analyte to go pass through the column compared to the mobile phase or a compound that is not being retained by the stationary phase. And usually we want this retention factor to be somewhere between 2 and 20. 2 because we don't want the compounds to elute very close to the dead time. This is both to get a good resolution as well as to avoid interferences from the compounds that are not interacting with the stationary phase. For example, here you also see kind of a heartbeat here at the dead time. And this is a very common thing to see in chromatography, because samples always contain something that is not interacting with the stationary phase, and this kind of heartbeats may occur due to that. Or if we don't see heartbeats, then we could just see small peaks that come from the fact that there were some compounds that didn't interact with the stationary phase, but they do give a signal in our detector. So in order to avoid any interferences in this region, we usually want our peaks to elute slightly later, so at least with a retention factor of 2. The retention factor is suggested to be less than 20 simply because usually above this we don't gain much in the resolution of the peak, so usually we can't make our chromatography better even if we make the retention factors even longer. Retention factor, by the way, is not influenced by the column length. So if we make the column twice longer, then the retention factor for the same compound, for the same mobile phase, for the same stationary phase should stay the same. However, it can still make our resolution better by just providing more time for the separation. Now, you might figure how then to identify the compounds. Okay, we separate these columns, but how do we know which of the compounds we are actually measuring then with the detector that comes after the column? Usually the detectors are relatively unselective. So this means that they don't really allow us saying what compound this was. A slight of an exception is mass spectrometry, where we can obtain at least some clues which compounds they are eluting, but absolute certainty we usually don't gain even with the mass spectrometer. Therefore, what we do is that we use analytical standards of the compounds that we want to measure, and we register the retention time of the compound we are interested in quantifying. Or just detecting. We measure the retention time, and then we analyze our samples and see if there are any peaks with the same retention time as we observe for our analytical standards of that compound of interest. So let's look at this visually. So if we start by saying, okay, we are interested in this compound, we take the analytical standard, or we order the analytical standard, we do the solution of this compound, we inject it to our chromatographic system, and we register the chromatograph. Then we see ideally one nice peak, and we see we can also determine the retention time of this compound of interest from the chromatograph. Then we can also take the samples that we are interested in analyzing, and we can chromatograph these samples by, in the same way, injecting the sample to the chromatographic system. It's very important that we keep our chromatographic system as similar as possible to the time when we were chromatographing the standard. So this means that we use the same column, we use the same mobile phase, and we also use the same mobile phase speed. So the mobile phase is traveling through the through the column with the same speed. And only these the retention times from the standards are also applicable for the samples. And here, for example, when we have a sample, we can see, aha, in the sample we have 3 peaks, and without the analytical standard, we wouldn't be able to say which one of these is actually our analyte. But because we before registered the retention time, and we know that we are expecting the compound to elute over here, then we can say that, okay, this peak here is the peak that belongs to our analyte. So we can detect this compound and also potentially quantify. And if we have another sample, but we do not see any peak at the expected retention time, which we saw for the analytical standard, then we have to say that in this sample, our compound is not present. So the identification of the compounds is based on the analytical standards and the retention times of the compounds measured from these analytical standards. Now, on the last example, you saw that for this mid sample here, the compound that we are interested in, so the blue peak, is actually not super well separated from the green peak. So we see that they are slightly merging into each other. And this, as you might guess, is not a very good chromatography. And in order to describe the goodness of the chromatographic systems, we have 2 parameters that are very important to obtain the best possible separation in chromatography. These are selectivity and efficiency. So selectivity is the ability of the chromatographic system to separate the compounds, while efficiency is the property of keeping the peaks as narrow as possible. And let's see this on a graphical example. So here are 4 chromatograms. And you might think which ones you can use for the actual analytical separation of different solutions and which not. So what do you think? So hopefully you figured out that the one on the bottom right is not very good. So we see 2 things. First, the peaks are actually not separated. So the peak tops are very close and the peaks are also very wide. The situation is slightly better if the peak tips are being pulled apart more. So we actually start seeing 2 peaks, but they are not really fully separated. And the situation is also slightly better when we make our chromatography more efficient. So the peaks become narrower, but still again, the peaks are actually not separated. However, if we achieve both narrower peaks and peak tips being pulled apart more, then we get a nice chromatographic separation. And when we put this in the terms of efficiency and selectivity, then selectivity means that the peak tips become more separated, while efficiency means that more efficient chromatography is when the peaks become narrower. So both of these need to be reasonable for us to get a good chromatographic separation. Now, how to measure this selectivity and efficiency? There are 2 important parameters, the resolution and selectivity. So if we have here a chromatogram with 2 compounds, compound A and compound B, then for both compounds, we have the retention times of these compounds, and we can also characterize the efficiency of this chromatography by the peak width. So we can look at what are the peak width of these compounds on this chromatogram. And resolution is a combination of both selectivity and efficiency. So in resolution, we take into account the retention time difference of these compounds. So the retention time of compound B minus compound A. And we divide this by the 0.85 times the sum of the peak width at the half peak height. So this W1 W half means that the peak width is measured at the half height of this peak. And with this, we get to resolution criteria. So we see how well resolved these peaks are. And we can also just alone characterize selectivity. And selectivity is the ratio of the retention factors of the peak B and peak A. The resolution needs to be higher than 1.5 to achieve baseline peak separation, but it's usually better to have the peak resolution of 2 to be certain that even if the peaks become a bit higher and at the same time a bit wider, they still don't collide with each other. The selectivity needs to be above 1 to be theoretically separatable. However, selectivity alone does not tell if the peaks actually are separated. It's rather a theoretical concept if these two compounds could be separated with this chromatographic system if sufficient efficiency is achieved. Efficiency can also be described alone, independent of the selectivity, and this is done by the number of theoretical plates, so the theoretical plate height. Theoretical plates sound very funny, and it has actually a long history already from the times where compounds were primarily separated by distillation, and therefore this is just an historical name, but a very cute one. So the theoretical plate number is something that we can think of as the number of times that this compound was retained by the stationary phase and was released again. Retained and released, retained and released, retained and released. And this can be calculated as the ratio of the retention time divided by the peak width at the baseline in the square up and then multiplied by 16. And or when we use instead peak width at half height, then we can just use a different coefficient. Either of these equations are valid, and the transformation between these two ways of calculating is based on the fact that our chromatography peaks usually have a Gaussian shape. So the numbers of theoretical plate is something that is very strongly varying depending on which kind of chromatography we are dealing with. In case of gas chromatography, especially capillary gas chromatography, or gas chromatography with capillary columns, the numbers of theoretical plates can be very high, reaching hundreds of thousands, while in liquid chromatography, we are usually dealing with 10,000 theoretical plates or more, but definitely less than in gas chromatography. Another important measure, which is less affected by the column length, is the theoretical plate height. And this can be used to compare the efficiency of chromatographic systems where we are using where we are using columns of different length. And this is then the theoretical plate height. And this is just the length of the column in millimeters or micrometers divided by the number of theoretical plates for this system. What is important to mention here is that the number of theoretical plates will slightly vary from compound to compound, but for isocratic elutions, so cases where we used throughout the chromatography, we use the same mobile phase, then this is relatively stable for all of the compounds. We will look at these different elutions more specifically for gas chromatography and liquid chromatography in the later lectures, as these are system specific. So all in all, the theoretical plate number as well as theoretical plate height are the most useful measures of describing how efficient is our chromatographic system. So this was a quick introduction to the chromatography parameters, and in the next video we are actually going to talk why peaks are even wide in the chromatographic systems and what are the factors affecting how wide they are.